Okay, so I should start by saying that I am an organizer just in name. The main organization was done by Mahan and Rajesh first, and then Naru. So I thank them for letting me speak here. So this is a talk about modular forms, and until about 20 minutes ago, I had no idea which modular forms are going to come up in the proof. So let's see. I hope my talk is not a completely sort of useless in terms of what's going to come up in next talk. So as told, I should also define Seegel modular forms. So let me start with the definition of Seegel modular forms, and then in the end we'll just very quickly we'll just specialize to elliptic modular forms, and then look at some concrete statements and examples for those. Okay, so n is an integer, and then I want to define degree n Seegel modular forms. Okay, so when n is 1, you just have usual modular forms, or what are called elliptic modular forms. Okay, so I'll define these. So I start with a group SP2NR. So symplectic groups, so these are all matrices such that M, J, M transpose is J, where J is this 2n by 2n matrix, which is given by a block of 0, n by n block of zeros, and then an n by n identity matrix, and then minus in 0. So SP2 is simply SL2. This can be checked easily. Okay, so that's my group, and then I'll be interested mostly in SP2N, well, this or this. Okay, so this is just a subgroup of SP2NR, and then I want the Seegel upper half plane, which is so a complex matrix, which I will write as this, so real part and complex part, so real part and imaginary part. So and C such that Y, which is the imaginary part of Z, is positive definite. Okay, so again, when n is 1, you just get the usual upper half plane. So I'll when n is 1, I'll forget about all these subscripts or superscripts that I'm going to put. Okay, so this is the Seegel upper half plane, and then SP2NR acts on the Seegel upper half plane as usual. So gamma, I can write it as a so each of this ABCD is an n by n matrix. Then gamma acting on Z is AZ plus B times CZ plus D inverse. Okay, so this is the usual Mobius transformation when n is 1. Okay, and because it's a matrix, I have to be careful where I put my inverse. Okay. So I'm soon going to define modular forms, and the name comes because these are moduli spaces. So here's a remark, if you don't know this. So Hn over SP2NZ, this is moduli space of principally polarized abelian varieties. Okay, I won't say much. So when n is 1, you have H over SL2Z, and you get, so this is isomorphism classes. Isomorphism classes of elliptic curves. Every elliptic curve has a principal polarization, so I don't need to say that word here. And how does this go? So tau in this direction goes to C mod Z plus Z tau. So this is an elliptic curve, can be made into an elliptic curve. So I take this lattice and then mod out by this. Conversely, if I have an elliptic curve, this is given like this, where this is Z W1, Z W2, chosen in a particular way so that okay, imaginary part of W1, W2 is greater than 0. So you can always find a basis like this, and it's not, yeah. So you have to mod out by this to get a one-to-one bijection. Okay, so these are moduli spaces of something, and so the functions or sort of some functions related to this are called modular forms. Yeah, okay, so at this point, I guess I should define what a congruence subgroups are. So, okay, yeah, so I think even now it's sort of, well, yeah, okay. So gamma n, I mean, maybe I should put a subscript n here. So these are all m in sp2nz such that this is congruent to the identity matrix modulo n. Okay, so these are some specific subgroups, and a congruent subgroup is any subgroup of sp2nz which contains this as a which contains this for some n. So those are congruent subgroups. If gamma contains for some n. Okay, so one example that sort of is interesting is gamma 0 n. So this is all m such that m is congruent to an upper triangular matrix mod n. Okay, so these are sort of some interesting examples of congruent subgroups. Okay, so so these are congruent subgroups. Then I want to define what cusps are. Okay, so I think already I'll just do this for n equal to 1. Yeah, I'll soon anyway specialize to this. So H mod gamma for any congruent subgroup, this is not compact. You can compactify it by putting cusps. So by taking sort of gamma and then H union P1Q. Okay, so any element of P1Q you can write as X comma Y. So this is sort of up to scaling by same non-zero element of Q. This is well defined, and you can, and the action is given by the matrix multiplication. Okay, so this is the action. And the fact is that, so I'll denote this is, so this is my notation, and gamma 1 acts transitively on P1Q, so you can take any element of P1Q and you can map it to infinity, for instance. And so gamma 1 H has only one cusp at infinity. So I'll use both these facts a little later, again and again, I think. Yeah, okay, so cusps. Good. Okay, so now we come to the definition of modular forms. It's sort of comforting to have something in hand. Okay, so slashing operator. You can define more general modular forms or, when n is bigger than 1, but I'm just going to do the parallel weight ones. So f is a function from this and k is an integer, then you can define this as cz plus d determinant to the k f of gamma z. Okay, so that's the slashing operator. So if you slash f for weight k, then this is, oh, sorry. Okay. Okay, so definition of function f from Hn to C is called a Seegel modular form if, so Seegel modular form of weight k level gamma for some congruence subgroup gamma if three things are satisfied. F slash k, well, so let me stick to my notes and write f is holomorphic, okay, on Hn. Two is f slash gamma is f for all gamma in this congruence subgroup gamma. And third is f is bounded in y greater than or equal to y. So I fix some y0 for all y0. So you fix any positive definite y0 and then f is bounded in this. So as you go towards infinity, it's sort of bounded. So that is what it means to say that it's holomorphic at cusps. Okay, so another way of saying this is it's holomorphic at cusps. Sorry? Yeah, so maybe I should, because I wrote down the definition only for SL2Z and I'm sort of improvising. So yeah, so this is sort of holomorphic at infinity, and then I want other cusps as well at infinity cusp. And so same for f gamma in SL, okay, SP2N R, so that we get holomorphicity at all cusps. Okay. Okay. So that's that. That's the definition. Okay. So from now on, I'll just stick to n equal to 1. So I'll really follow my notes until the end when I have to define these U, V, and W that appeared in the last talk. Okay. Okay, so from now on, n is equal to 1, and so all these subscripts and superscript, whatever have appeared up to now, they'll disappear. Okay, so so when n is 1, sort of the statements are simpler, and the proofs are more concrete. But most of the things with sort of appropriately modified statements, most of the statements sort of have generalizations to n bigger than 1. Okay, sort of arithmetically, of course, some things are harder, like Galois representations and something. But okay, so so Fourier expansion. Okay, so for any congruence subgroup gamma, 1, n, 0, 1, so for an appropriate n, this always belongs to there because this belongs to gamma of n. Okay, and so this means that f of z plus n is f of z by the slashing. So f is a modular form, and then it doesn't matter what the weight is, this always works. So in particular, when capital N is 1, you have f of z plus 1 is f of z, which is the thing that was used for phi 0 in the previous talk. Okay, so then f has a Fourier expansion. So f of z is summation n in z. So I'll say, oh, what about this? E to the 2 pi I z n by capital N, which I'll also write as a n q to the n by n. So q is e to the 2 pi I z. Okay, so and f holomorphic at infinity implies a n is 0 for all n less than 0. Okay, so this is another way of saying that that f is holomorphic at infinity. Okay, so this is Fourier expansion. At infinity, and then you can get Fourier expansion at other cusps by so let C be possibly another cusp of gamma mod h. Let gamma be such that so gamma infinity is C, right? So this will be in SL2, right? Because SL2Z acts transitively on P1Q, and so Fourier expansion of f at C is the Fourier expansion of f's at infinity. Okay, so this is how you get Fourier expansion at all cusps. You have to be careful about choosing this gamma. I mean, yeah. So these coefficients may depend on the choice of gamma, but a lot of things like whether something is non-zero or not doesn't depend on the choice of gamma. So if I make some statement about Fourier expansion at other cusps, then you just have to be a bit careful. Okay, so So F is called, again, so holomorphicity at all cusps means that, that the Fourier expansion of this has no negative terms. Okay, so I won't write that down. F is called a cusp form if A0, or maybe I should write A0. So if A0 is 0 at all cusps. Okay. So another way of saying this is Fourier expansion of F at all cusps has no constant term. Okay, so these are cusp forms. So in a while we'll see examples of modular forms, and there will be two kinds. One will be Eisenstein series, which are not cusp forms, and then we'll see this delta, Ramanujan's delta function, which is a cusp form, and then the theta series, which is often a cusp form. Okay, and incidentally, these are all the examples that we know explicitly. Okay, so there are other cusp forms, but it's not, we don't know how to write them down explicitly in terms of coefficients. Okay. All right. So here's a piece of notation. This is the C vector space of modular forms of weight k, level gamma. Okay, so mk gamma 1, this is full level. Okay, so this is called full level. Okay, level 1. Okay. All right. So what do we know about this? So fact, and I'll prove this in a special case. So dimension mk gamma is finite. So this is for any congruence subgroup gamma. Okay. By the way, before that, I should make a remark. So this SL2Z modulo plus minus 1, this is generated by, so in the previous talk there were two kinds of modular relations used, and in fact these are all the ones that we need. So this is generated by two elements S and T, and with two relations, S square, ST cube is identity. And what is this S and T? So S is the one that appeared before, and then T is also, I think, appeared before. Okay, so to check that something is a modular form of full level, you just have to check I mean, so the modular relations I'm writing down. So f of z plus 1 is f of z for all z in H, and f of minus 1 by, yeah, I mean, because I'm modding out by minus 1. So z to the k f of z. Okay, so so it shouldn't be surprising when that somehow you only use these two ever in certain proofs. Okay, where do I go next there? Okay, so all right. So I want to show that fact about finite dimensionality for full level. then, so in fact, so theorem, dimension mk, so mk gamma 1 is 0 if k is less than 0 or if k is odd. Okay, so this is this will be sort of right. So because if k is odd, you would where do we go? So by so by taking minus one minus, I mean, by taking something like this, you would get that f of z is minus 1 to the k, and if k is odd, then you get f of z is f of minus z. So when k is odd, you don't get any non-trivial forms. And when k is negative, you can show that it's again 0. So the only thing is even positive, even non-negative integers. So the formula for this is the largest integer less than or equal to k by 12 plus 1. This is if k is not congruent to 2 mod 12, and then k by 12 if k is congruent to 2 mod 12. Okay, so what the hell? Okay, so there's these two kinds of things. Okay, so I'll sketch a proof of this very briefly. So first step is to show inequality. Okay, so and then the equality will be shown after I introduce Eisenstein series. Okay, so how does the inequality? Inequality. So first thing is to show this. That the dimension is less than or equal to this, and this already shows why these two cases appear. Okay, so what do I do? First, I have to tell you what the so there's this famous picture that you see in sort of most modular forms book or all modular forms book. Fundamental domain for the action of gamma 1 on H. And so what does it look like? So there's minus 1, 1, 0, minus half, half. And then there's a circle of radius 1 here. There are these two lines. So this thing, this is the fundamental domain. And this is just all z in H such that, yeah, so mod of z is bigger than 1, and real part of z is less than half, and you should, and then f1 tilde, this also, you should include the sort of this boundary. Okay, so things here are equivalent to this, and things here are equivalent to this using, so this is equivalent to this using T, and this is equivalent to this using S. Okay, so this is with this half boundary. Okay, all right. So so I want to get back to the proof now of this inequality. So f is not a function on gamma mod h mod, I mean gamma over h. So f is not a function on gamma 1 mod h, but for any p in gamma 1 over h, the order of vanishing of f at p is well defined. Okay, so at infinity, you would just take the Fourier expansion and look at how this is also well defined. Okay. So you would just look at the Fourier expansion and see what's the smallest n such that an is non-zero. Okay, so the first thing we prove is to get the inequality, and this is the main step anyways, is that summation p in gamma 1 over h odd p of f plus odd infinity of f, this is equal to k by 12. Okay, so that's the thing that appears. And how does this proof go? Well, you look at all the possible zeros of f inside the fundamental domain. So I should say something about the stabilizer of each point. So, yeah, why does this k by 12 come? So, stabilizer in gamma 1 of each point of f1 tilde is trivial except for omega, which is the cube root of -1, so here, and then I, so fourth root of -1, which is I. And so what is the stabilizer of this? So I always get, so this is ST, I think. Yeah, so the stabilizer of this is generated by ST, so it's an order 3 group, and the stabilizer of this is generated by S. Okay, so those are the stabilizers. And so what this means is that this is not smooth. Okay, it has singularities at these two points, which is what sort of gives you the dimension that you want. Okay, so it's been half an hour. All right. So okay, what do I want to say about the proof? So what you do is you look at all the zeros and zeros of f, okay, in this region, and you remove a small disk around each zero. So it could be on the boundary, it could be here, and you remove a small disk around these, and then then sort of you get a that's your cycle, right? So you have this, and then you have some things removed, and union of this, and so on. So that's your cycle, and you use Cauchy's theorem to say that the sort of the order of zeros everywhere. I mean, if you integrate d log f on that cycle, you get 0. So you use that, and then you actually integrate it. So what happens is that you can, if you want a finite domain, you can cut off somewhere here, and the integral over that is, so the integral over this cancels the integral over this. The integral over this is same as the integral over this. So the integral over this you can show is pi I by 6, I think. And then the integral over this is, so the integral sort of at the line you cut off is odd at 2 pi I times odd at infinity. So when you plug that in here, and simplify, you get what you want. Okay, so that's very roughly, so for this you use apply Cauchy's theorem to d log f, and sort of this okay, yeah, so there are some zeros, and there could be zeros here, so this is kind of the cycle D, and D. You also include this kind of somewhere far away above which there are no zeros. So that's my D. Okay, so the idea is sort of quite simple. One, you can work out from there. Okay. Yeah, you go from here to here, right? Yeah, so that's why when you integrate over this, you get sort of pi I by 6, which is the 30 degrees. Yeah. Okay. All right. So how do I get the so assuming this star? How do I get the inequality? So I take some p1 up to pm plus 1. So what is m? M is this number k by 12 plus 1, non-elliptic. So which simply means that it's not in the orbit of omega or I. And then, yeah, m points, okay. Yeah, m points. And let f1 up to fm plus 1 be some modular forms, be given. Then there exists a linear combination f, which is there exists f, which is vanishing on p1 up to pm, okay, and not all AIs are not all AIs are 0, okay, but this, because of this inequality, this implies that f is 0. Oh, I should have said f is non-zero here. Okay, so this implies that because yeah. Sorry. No, this is, I should, what is this NP? This is the order of stabilizer of P. Okay, so it's either 2 or 3. Sorry, yeah, that's important. Because when you integrate around this point, you sort of have to, you're not integrating over the full circle, you're just integrating over this or this. Yeah. Okay, so, but I have avoided those points, so this is still unchanged. Okay, so this implies that f1 up to fm plus 1 are linearly dependent. Okay, so that gives me the inequality. That gives me the inequality I want when k is not congruent to 2 mod 12. And when k is congruent to 2 mod 12, you can do slightly better by seeing that because this is an actual equality here, this can only happen when there is a simple 0 at omega and I, and so you can do slightly better. So done for k not congruent to 2 mod 12, and for k congruent to 2 mod 12, if there is a Yeah, okay, nothing written. If sort of 1 by 3 and 1 by 2 appear in the sum. Okay, so yeah, it's just, you just have to figure out that you need to have an equality, and so that's the only way equality can appear. Okay, so you can do one better in the dimension. And later on, we'll see sort of in weight 2 or 12k plus 2, there's something, I mean, this Eisenstein series is not holomorphic, so that's sort of another explanation. Okay, anyway, so we have shown the step 1 for the theorem, or roughly. Now, okay, now we should see some examples of okay, so now let k be bigger than or equal to 4 for this. So, so these are all sort of different avatars of same or very closely related things. So the first way, okay, so I want to define some function which has certain kind of invariance property under gamma 1. Okay, and if I were in a finite group, I know how to do that, and you try to mimic this over infinite groups, and then sort of it works, and this kind of thing works very generally. So here gamma infinity is plus minus 1 n 0 1 okay, so this is a subgroup of gamma 1. And then I take this infinite sum, and you can work out what this infinite sum is. This is half summation C d in Z2 such that GCD of C d is 1. So in particular, they are not both 0. 1 by CZ plus D to the k. Okay, so that's my normalization. All right. So one can work out that this sum is actually this by the slushing operator. So, and this converges as k is bigger than or equal to 4. Okay, so there is a problem when k is equal to 2, and we'll come to that a little later. And by the virtue of the definition itself, you can sort of see that Ek of Z, this belongs to Mk of gamma 1. So we have a modular form of weight k for each even. Yeah, I mean, of course, if k is not even, this just turns out to be 0. So most of the time when I write k, it will be even. Okay. Okay, so that's one way of defining. That's our example. That's one way of defining an Eisenstein series, and there are other ways of defining. So, by the way, this sort of works even for Seegel modular forms, and you get what are, so you have to take again some unipotent, and then and then you can define this kind of thing, and you would get Seegel Eisenstein series. There are of course more general Eisenstein series on when n is bigger than 2. I don't know if we need any of those, but it's just a comment. So you can also define gk of z. This is half of mn in Z2. So a summation prime means that not both m and n are 0. Okay. So the prime always means that this is a non-zero pair. Okay. And so again, this converges absolutely when k is bigger than equal to 4. And in fact, there is a simple relationship between this and ek. So this is the zeta function, the Riemann zeta function. And why is this true? Because you can, if m and n are not co-prime, you can pull out r to the pull out the common factor from it, and you get sort of the common factor is g, then you get g to the k. And so that appears in the sum, and because everything is absolutely convergent, you can sort of rearrange and you get this. Okay. So this is another. So this is also an Eisenstein series. So this also belongs to mk, and they are proportional by this factor. So it's basically the same thing. And then there is a nicer one, sort of, especially if you're a number theorist, then this is k minus 1 factorial 2 pi I to the k of gkz. Okay, so the bold-faced gk is this. And why is this nicer? Because its Fourier expansion has rational coefficients, as we'll soon see. So this is again they all live in the same one-dimensional subspace of mk gamma 1. Okay, so these are all the examples we know at the moment. Okay, now what am I going to do? I'm going to tell you what the Fourier expansion of these things are, I think. No, I'm going to complete the proof of that theorem. Okay, so m star gamma for any congruence subgroup gamma is by definition okay, so it's the direct sum of all the modular forms of all weight. And so you can multiply two modular forms of weight. So modular form of weight k1 and k2, and get a modular form of weight k1 plus k2. So this is a ring. Okay? And the proposition is that m star of gamma 1 is isomorphic to the polynomial ring generated by E4 and E6. Okay, so okay, so how does one prove this? So basically, because of the dimension bound that we had earlier, it's enough to prove that E4 and E6 are algebraically independent. Then you can check that any modular form of any particular weight k, even weight k, can be obtained as a linear combination of monomials in E4 and E6. And those are all because of the dimension bound that we had. Okay, so enough to prove that E4 and E6 are algebraically independent. And to show that, it's enough to show that. So first step is E4 cubed and E6 squared are not linearly dependent. So are not linearly dependent. Okay, and how do I show that? So I take f, which is E6 by E4, and then f squared. So this has weight 2, right? So f squared is E6 squared by E4 square. Now if E6 is so if E6 squared is lambda times E4 cubed, then I get lambda E4, which implies that f is holomorphic. Okay, and it's non-zero, right? F square is holomorphic, so F is holomorphic, which implies that that M2 gamma 1 is not equal to 0. So this is not true because of the bound we had earlier. Okay, so the bound for k equal to 2 was k by 12. Okay, so the integer less than or equal to k by 2. So that's 0. Okay, so they are not proportional. And then we have, so let's say that P of xy such that P of, so in fact this works for any two modular forms which are not proportional. Okay, so two non-zero modular forms which are not proportional, then this implies that this is 0, where this is the homogeneous degree d part of P. Okay, so homogeneous degree d part. So this you can just figure out by looking at the, so F1 and F2 have the same weight. And so this works by just looking at the weight. So each weight part should be 0 in itself, otherwise that doesn't work. And so this implies that P of F1 by F2, which is F2 to the D, P of F1, F2, this is 0, which, but this is a complex polynomial, so it has only finitely many zeros, so it means that F1z over F2z only takes finitely many values for all z in upper half plane, which means that takes only finitely many values, but it's a meromorphic function, so it should be constant. So this implies that F1 over F2 is constant. Okay, so this means that E4 cube and E6 square are linearly, are algebraically independent, and so E4 and E6 are algebraically independent. So in particular, this sort of shows the proposition as well as our theorem from before. Yeah, I'm assuming that they have the same weight. So I'm applying this to E1 cube, E4 cube and E6 square. Yeah, I said that orally. So this implies the proposition and dimension formula. Okay. All right. So I have to tell you Fourier expansion of Eisenstein series, and then that will lead me to defining what the, okay, so I'll give you the Fourier expansion of this, which I said is what number theorists like better than other things. So this is so the constant term is a Bernoulli number divided by minus 2k plus some non-constant terms. And what is bk? So bk is defined by x by e to the x minus 1 is summation k going from 0 to infinity bk x to the k by k factorial. So this is how this is what defines the Bernoulli numbers, and they are rational numbers. And sigma k minus 1 of n is summation over all positive divisors of n d to the k minus 1. Okay, so that's the divisor function. So, so the nice thing about this is sort of all the non-constant terms are really simple, and then the constant term is some Bernoulli number, which is complicated in the sense that it's related to values of zeta function. And so this is how Eisenstein series play an important role in number theory, because you can understand the values of zeta function by studying these Eisenstein series. Okay, and so this is a general theme for other automorphic forms as well. So there are Eisenstein series over other groups, and again the same kind of phenomena happens, that the constant terms are related to L values. The non-constant terms are usually not this simple, but they are related to L functions, which are sort of appear as on the smaller groups. And so you can sort of do an inductive process if you like. Okay, so all right, so I wanted to give a proof of this, but maybe that's not such a, I'll do it anyway. So here is a sketch. Okay, and so this might look completely unmotivated. Why one looks at something like this, but sort of it, I'll only quote a sentence that appears in the book of Diamond and Sherman on modular forms. So you have to use this kind of thing. Okay, so this pi cotangent of pi I. So you have to use this formula, it's a well-known thing. And then you have to use Fourier expansion for this, which is 2 pi I times summation m going from 0 to infinity, q to the m. So again, q is e to the 2 pi I z. Tau, yeah, pi tau. I don't know why I had I there. And q is, now I've changed my notation, so z became tau for some reason. Yeah, so this, you have to use this, and why do you have to use this? So Diamond and Sherman say that this is a standard rite of passage in the theory of modular forms to learn how to use this kind of thing. So, so they don't give any motivation for this. Okay, so you differentiate this k minus 1 times, and you get summation d in z 1 by tau plus d to the k equals minus 2 pi I to the k minus 1 factorial summation m going from 1 to infinity m to the k minus 1 q to the m. So this is what you end up with. And then if I do 1 by c tau plus d to the k, so again, this is a summation prime, so over non-zero things, then this is equal to summation. And here I'm sort of freely using that things are absolutely convergent. So, so you will see in a minute when I define the weight 2 Eisenstein series that you have to be more careful when you do the weight 2 thing. C tau plus d to the k. Okay, so so this one is a bit like that, and so when you when you substitute, when you use this formula for this, you get what you want. And here you have 2 zeta k plus 2 pi I to the k, k minus 1 factorial summation c going from 1 to infinity, summation m going from 1 to infinity, m to the k minus 1 q times cm. Okay, and then you simplify. So you basically you get the G2 without the bold face, but then you have precisely the the factor that you have to multiply by, or reciprocal of it, to get the boldface G2, and you have to use Euler's formula for the values of zeta function at even positive integers. So that's Bernoulli numbers times a factor like that, okay, up to some multiplication by k, division by k or something, okay. So that gives you the Fourier expansion of the Eisenstein series. So that's good. Okay, so now I come to Eisenstein series of weight 2. Okay, so the problem with the weight 2 Eisenstein series is that the sum that we defined for E sub 2, that wouldn't make sense because things are not absolutely convergent. But what does make sense is the Fourier expansion. Okay, so G2 of Z, which is minus 1 by 24 plus summation sigma 1 n q to the n, this converges rapidly enough. So this makes sense. And so we forget about the E2 and we just take this. So we define E2 to be, or if you like, we define G2 to be minus 4 pi squared, this bold-faced G2, and we just define E2 to be 6 over pi square of, so this zeta factor, zeta function appears. So I'm using zeta 2 explicitly here, or 1 over that, yeah. So these make sense, and in fact you can also make sense of a okay. So here's a proposition that I think should be attributed to Hecke. G2 of Z, so this makes sense. So this is half. So you can write it in terms of this lattice expansion if you are careful with your summations. So summation n not equal to 0, 1 by n squared plus a half times m not equal to 0, summation n in Z, 1 by mz plus n squared. Okay, so this makes sense, and sort of why I write this as a proposition is sort of you're not allowed to change the order of the summation, so you take this and then you do this, and now things converge, but not absolutely. So you have to be careful, but you can show that the Fourier expansion of this is minus 4 pi squared times this by using the same kind of argument as you do here, but you have to be very careful about what you are doing at this step. Okay. So this is same as before with more care. But the more interesting thing for us is what happens when you do the modular transformation. So A, B, C, D, this belongs to gamma 1. So what is this? This is just CZ plus D squared G2 of Z minus pi I C CZ plus D. Okay. All right. So it doesn't quite behave like a modular form, but it has this extra factor, and so yeah, I have some remarks somewhere. Yeah, so this is like so this is not a modular form, but it's a quasi-modular form. Okay. which I'll define in a moment, and then it will be clear what I mean. Okay, so how does one prove this? So if you have to use Hecke's trick, this sort of appears sort of everywhere when you study Eisenstein series. So you introduce an extra factor epsilon. I'm just using the notation from Zagier's book. Usually it's denoted as S, I think. So you put an extra factor there. So this was already there, and then you take mz. So my z and tau's keep interchanging, I think. 2 epsilon. Okay. So now, as long as my epsilon is bigger than 0, this converges absolutely, and I can do whatever I want with it. In particular, I can show the following modular transformation. So in particular, I can show that G2 epsilon AZ plus B upon CZ plus D, this is equal to CZ plus D squared, CZ plus D 2 epsilon G2 epsilon Z. Okay? So it does behave in a way that I want it to behave. And so this is one. So this is easy. I mean, you just have to, you can interchange summation and so on. So you can do this. The other one is more tricky, but I'm not going to show this. G2 epsilon Z. So this is the more interesting one. This is G2 Z minus pi over 2y. So y is imaginary part of Z as always. Okay, so putting those two together, you get this kind of thing. Okay. So that's the weight 2 Eisenstein series, and that's the modular property of weight 2 Eisenstein series. Okay, now I'm going to define what quasi-modular forms are. And before that, I'll define what almost holomorphic modular forms are. Kind of cheap definition of quasi-modular forms is the following. What's the notation for? Yeah, so M star hat. This is C, E2, E4, and E6. So that's one way of defining quasi-modular forms. You just sort of take the ring generated by these and say that these are all the quasi-modular forms. I don't know how useful that is. I've never worked with quasi-modular forms, so I have no idea whether this is any useful. This is of any use. But in any case, we have to define the following. So almost holomorphic. No, I think I'm using this definition, sorry, this notation. So M tilde is the quasi-modular forms. Okay, so MK hat less than or equal to P. So P is just some positive non-negative integer. So almost holomorphic modular forms of weight K and depth less than or equal to P, right? This is, yeah, it's not depth P, it's depth less, that's the terminology used, less than or equal to P. So this is all the functions on upper half plane which are of the form are going from 0 to P, FRZ minus 4 pi y to the minus r, so that 4 pi, I don't, this is just some normalizing factor you have, and then y. So basically these are polynomials in y to the minus 1, such that fr z is holomorphic, and capital F, this is f for all gamma in gamma 1. Okay, so capital F behaves like it satisfies the modular property, but it's not holomorphic. Instead, it's a polynomial in y to the minus 1 with holomorphic coefficients, holomorphic functions as coefficients. Okay, and then almost holomorphic modular forms are just unions of mk hat less than or equal to p. Okay, and the ring of almost holomorphic modular forms is just direct. So I've forgotten about gamma 1 now, because I'll only deal with full level. So these are almost holomorphic modular forms, and the ring of quasi-modular forms this is all f0 such that there exists f in with f equals f0 plus f1 minus 4 pi y inverse and so on. Okay, so it's the constant term of some almost holomorphic modular form. So these FIs need not be modular forms except for the highest degree non-zero term. Okay, so that's a holomorphic modular form of weight k minus 2p. Okay, so quasi-modular forms are sort of holomorphic functions which appear as constant term of some almost holomorphic modular form. And I'll write down two facts, which is that m star tilde going to m star or hat going to, this is easier to define. So this is summation fi to the minus I. This going to f0 is an isomorphism of rings. So an almost holomorphic form is in some sense determined by what its constant term is. And then if f has depth p, which means that fp is non-zero, then fp is a holomorphic modular form of weight k minus 2p. So this is used a little bit later. Okay. All right, so modular forms, Eisenstein series, and then quasi-modular forms. So examples, the only example that I know is E2, and so I'll write that down. So for G2, G star is G2 minus pi by 2y. Okay, so this is my polynomial in y inverse, so degree 1 polynomial in y inverse with G2 as the constant term, and then the appropriate thing. So 1 by 8 as the coefficient of the degree 1 term. So this is an almost holomorphic modular form of weight 2 and depth 1. Okay, and so G2 is a quasi-modular form. And so E2 and this bold G2, they are all quasi-modular forms. Okay, so the next thing I was told I have to say is this proposition in in Zagia's book, which is about how what happens when you apply some differential operators to quasi-modular forms. So when you apply these differential operators to modular forms, you don't get modular forms back. They lose their holomorphicity, and so you have to go to the bigger space of almost holomorphic modular forms or quasi-modular forms. Okay, so here is some differential operators. Okay, so df, which I sometimes also denote like this, which is, it's just q df by dq. So if I apply this to Fourier expansion like this, and what happens is that f prime of gamma z, yeah, sorry, they also lose their sort of modular property. So this is cz plus d k plus 2. Okay, so f is a weight k modular form. Then so the weight gets shifted, as well as some funny term is added, 2 pi I c cz plus d to the k plus 1 f of z. Okay. Yeah, so this kind of thing happens. So you have to go to the space of quasi-modular, I mean, almost holomorphic modular forms or quasi-modular forms. And so the following proposition holds. So D, if you apply this to weight k and depth at most p almost holomorphic forms, you still get almost holomorphic modular forms. You just have to go to a different depth and a different weight. Okay, so you can already see this from a formula like this. Moreover, you can write every. So this by the way, this I should say that this proposition holds for any congruence subgroup. I'm just doing it for level 1. Okay. And so in the second step, I have to, if I do any congruence subgroup, I have to say what is the replacement for E2. Anyway, so if I take depth at most p, weight k almost holomorphic forms, then I can write them as a polynomial in E2 with coefficients which are given by particular modular forms. Okay, so here I had gamma 1, so let me keep that. So these are holomorphic modular forms of weight k minus 2r and E2 to the r. Okay, so I can write every almost holomorphic modular forms like modular form like this. And then yeah. Oh. Ah. What am I doing? No, I think I want tilde. I want quasi-modular forms everywhere. Yeah. So Sorry, I did, sorry, just a minute. So I did not define the notation with sort of depth less than or equal to p, but you can imagine what it means. This f has to belong to m hat k less than or equal to p. Yes.
So the differential operator d, here,
yeah.
equal, more or less equal to the differential c.
Yeah.
Because,
right, so it's 2 pi I sort of d over dz. Yeah, this is why it's sort of this notation is there. Okay, what else? Yeah, sorry, I want tildes everywhere here. Yeah. Yeah, so any quasi-modular form of weight k and depth at most p can be written like this. Yeah, sorry, that's it. Tilde is sort of very important here. It's sort of not so important here, right? Mk tilde less than or equal to p. This is, so I can even obtain them by applying differential operators, and then maybe E2. So what happens is that if I am in small enough depth, so r to 0 to p, dr m k minus 2r gamma 1. So I have to apply it r times. If p is less than or equal, p is less than k by 2. So if I am in small enough depth, then everything is obtained like this. If not, then I have to use E2. Okay, so r going from 0 to k by 2 minus 1 dr m k minus 2r gamma 1 plus sorry, I mean plus meaning direct sum. I have to take this one thing, k by 2 minus 1 of E2. Okay. All right. So, okay. So I'll very briefly sketch a proof of 1 and 2, and then leave 3. So I said this can be done more generally with other congruence subgroups, but then I have to replace E2 by another quasi-modular form, which is not a modular form. So of weight 2. So I don't know how to show that there exists one, and then once there exists one, you can use that, I think. So yeah, I don't even know what the statement is. So Zagier doesn't say this explicitly.
it's still a module. I mean, if you get still over,
Oh, you cannot have others. Oh yeah, I mean, sorry, E2 is a quasi-modular form for other congruence subgroup as well, and so you just consider that as a, okay, yeah, great. So that. Okay, so how does the proof go? So here's a very brief sketch. So the first one, okay, 1. So I take f0, which corresponds to sort of f. Okay, so this f is summation fi minus 4 pi y to the minus I. So this is my quasi-modular form. So there exists an almost holomorphic modular form, whose constant term is this f0. Okay, and then there's this kind of derivative, which is, so this is by definition something like f prime of f prime minus 4 over 4, k over 4 pi y f. Okay, so that's my definition of this differential operator. So when I apply this to f, what I get is summation d fr plus k minus r plus 1 fr minus 1 minus 4 pi y to the minus r. Okay? So this implies that d of f0 is also, and the depth increases appropriately. Okay, so m tilde k plus 1. Okay. So I'll take, I think I'll take, keeping the tradition of last 2 days, I'll take 10 more minutes. The lunch is not going anywhere, I think so. Okay, so, all right, so sketch of 2, so here we use induction on P, and how do we do that? So we use this fact from here, that the highest, the leading coefficient is a modular form already. So F is summation, again, Fi minus 4 pi y to the minus I going from 0 to P, and Fp is m k minus 2p gamma 1. So the fact that you have to use is somehow E2 star is E2 plus 1 by y times some coefficient. I don't care exactly what it is. But this means I can write my f as Fp E2 star to the P. Okay, so I just raise it to Pth power, and then with some coefficient plus an almost holomorphic modular form of depth less than P. Okay, because sort of this is the depth P part of it, and then I then I write it, everything else. So then use induction on P. Okay, so that's the sketch of 2. So because you have an explicit expression for E2 star in terms of 1 over y, and that coefficient is non-zero, you can write sort of 1 over y to the p as in those terms. Yeah. Okay. Sorry. Yeah. So that's this proposition. I'm not sure exactly how this is going to be used, but this is there. Okay. And 3 is similar. You have to use induction on P again. So you isolate the highest term and you do play around with it. Okay, so this is all I wanted to say about Eisenstein series for the moment. So some more examples. So first one is so this sorry, n to I always get this thing mixed. So n to the 24. Yeah. So this thing. Yeah. So this is all I'll say. Okay. So I don't have time to show that this is a modular form of level 1 and weight 12, but maybe this is going to be useful at some point. So this is E4 cubed minus E6 squared. Okay, so this is another, I don't know if this you can take this as the definition, I guess, if that's useful. But this shows that this is a weight 12 modular form for full level. Okay, so that's one thing. And then the other thing which is kind of useful for the last fact that I'm going to state is the following. So this is easy fact thing. So if you have a if you take weight 4 times an integer, then this is the weight, the sort of degree k part of this. Okay, degree 4k. So what you do is this you assign sort of degree 4, and this is degree 12. So any monomial will have degree 4 times the power of this plus 12 times the power of that. And you can show that the weight 4k modular forms you can write in terms of monomials of e to the e4 and delta. So this you can check using this relation, for example, and this will be used later on. Okay. So theta series. So very, very briefly, so lambda is a lattice of rank m, and then we recall all the definitions. So lambda star, this is dual lattice, right? So all those elements of Rn which pair with lambda to give you an integral element. So this is dual lattice. Then we had the notion of unimodular. Lambda is unimodular if lambda is equal to lambda star, and lambda is even if q of x, which is half xx, belongs to z for all x in lambda. So we are interested in even unimodular lattices. That's what I wanted. Yeah, not self. I don't want self-dual. I think so. So you can define theta series generally for any lattice, but I'll just state the facts about that for unimodular, even unimodular lattices. So I can denote it like this, or I can denote it with the quadratic form that's attached to this. So this is all lambda in lambda q to the q lambda. So that's the Fourier expansion of this. So this can be written as 1 plus summation rqn q to the n. So here rqn is the number of ways in which n can be written as a value of q. Okay, and the fact is that if lambda is even unimodular, then this is a modular form of weight m by 2. M was the rank, remember, and full level. Okay, so if it's not unimodular, then it's not full level, and so on. So it's a bit more complicated, but it's always a modular form of weight m by 2 with some level. I mean, as long as it's self-dual. So. Okay, so what do I want to do? Oh yeah, so I want to, I want to state a proposition. One, so RQN is minus 2 over BK sigma K. Oh, what is K? K is m by 2 n plus big O of n to the k by 2. Okay, so this is as n goes to infinity. Okay. So in the n variable. Okay, so this is some expression for this. And then 2 is 8 divides m, or 4 divides k. So how is 1 proved? So theta lambda belongs to mk gamma 1, and you can, so this has only one cusp, right? So a fact which I stated very early on. So whatever the constant term of this is, you can kill it by subtracting some multiple of the Eisenstein series of weight k. That's why this factor appears there. So then after this difference will have no constant term at the unique cusp that gamma 1 has. And so it is a cusp form. And then there is a general result about the growth of Fourier coefficient of cusp forms. They are like big O of n to the weight by 2, and that gives this. Okay, so theta lambda minus 2k by bk gk is a cusp form. Okay, so this is a cusp form, and then we know that their Fourier coefficient grow like this. So that proves 1. This is a modular proof of 1, and so I think, yeah. Little, is it little o or big O?
Because cusp form will give you n to the k minus 1 by 2.
Oh, n to the k minus 1. Yeah. I think this is maybe easier to. Okay. Yeah. Yeah.
Big O will allow an Eisenstein.
Big O will. No, Eisenstein series has sort of k minus 1. K minus 1, right? It's not over 2. Yeah. I don't think this allows Eisenstein series. Yeah, k is at least. Okay, k is at least. I mean, yeah. Okay, where was I? Yeah, so if, so now 2, if k is congruent to 2 mod 4, then you can check that bk is positive. Yeah, and so for at least for this argument, this is good enough, because then r q n is less than 0 for n sufficiently large, which is absurd. So. Right, so that proves that k is 0 mod 4, and so m is 0 mod 8. Okay. What else? So yeah. So now, okay. So last thing I want to say is something about extremal lattices. Okay. So because the dimension of so now k is congruent to 0 mod 4. So dimension. So in particular, it's not 2 mod 12. So this is this. So this implies that smallest positive n such that there exists lambda with q of lambda equal to n satisfies n less than or equal to k by 12 plus 1. Okay, so this is the smallest possible non-constant Fourier coefficient of this. And so lambda, an even unimodular lattice lambda is called extremal if n as above equals k by 12 plus 1. Okay, so those are the extremal, these are extremal lattices, and examples of these are E8 and Leach lattice, as was mentioned by Abhinav a few times. But here is a theorem, and I should mention the names, I guess, for this. Not even sure if I got the spelling correct here of the first name. So there are only up to isomorphism finitely many extremal lattices. Okay. Even unimodular. Okay, so I'll just orally say what the proof of this is. So the dimension of the space is k by 12 plus 1, and so you can, moreover, you can write down, so this mk, which is divisible by 4, you can write down in terms of this E4 and delta, right? So you can write down this space in terms of E4 and delta, and you can construct, there is a unique modular form, I mean up to scaling, but there's sort of a unique form whose first non-constant term is precisely this n, okay, this nth term. So there's a unique one like that. And you write it down in terms of this E4 and delta, and you look at the nth term and the n plus 1th term, and what Seegel proved was that the nth term is always positive, and the n plus 1th term is negative for n large enough. Okay, so for n large enough, the n plus 1th term is negative, which means that this unique form that you wrote down here cannot equal your theta, right? Because for theta, all the coefficients of all the Fourier coefficients are positive, and because one of them is positive and the other one is negative, you cannot even multiply it by -1 to make everything positive. So that's I think that is roughly the proof of this. That's the idea behind the proof of this, and there is a effective bound for this, which is 160,000 or something. So you cannot have a lattice of rank more than 100 and let's say 70,000, which is extremal. Yeah, okay, so I'll stop here.